You drop your phone and it falls toward the ground. Why down? Why not sideways or up or at some random angle? If you say because of gravity, you're right. But what is gravity? Like, actually, here's the thing. The smartest physicists on Earth still argue about this question. Newton thought he knew. Einstein proved Newton wrong. And today? We're still not sure Einstein got it right either. The force that keeps you glued to your chair right now is one of the deepest mysteries in the universe. Let's start with what we can observe. Right now, you're experiencing a gravitational force toward the center of the Earth. That's what creates your weight. But here's what's strange. You're also pulling back on the Earth with exactly the same force. The Earth just happens to be 6 trillion kilograms, so it doesn't budge when you jump. This pulling happens between every single thing that has mass. You and your coffee mug are gravitationally attracted to each other. Your coffee mug and the lamp across the room are pulling on each other. The lamp and the building next door, the building and the moon. Everything with mass attracts everything else with mass, everywhere in the universe, all the time. But the force is incredibly weak. The gravitational pull between you and your coffee mug is about 0.1 pounds. That's a decimal point followed by 11 zeros. You'll never feel it. The only reason you feel Earth's gravity is because Earth is absolutely massive, about 13 trillion pounds. Think of it this way. Gravity is like having an incredibly weak magnet inside every atom of matter in the universe. Each magnet is pathetically feeble on its own. But when you collect 6 trillion kilograms of these weak magnets together, like in planet Earth, suddenly you get a force strong enough to hold oceans, atmosphere, and 8 billion people firmly in place. So how does this invisible pulling actually work? Let's build this up step by step. In 1687, Isaac Newton figured out the mathematical rule. He called it the universal law of gravitation, and it's beautifully simple. The gravitational force between any two objects depends on just 3 things: the mass of the first object, the mass of the second object, and the distance between them. Here's the key insight. If you double the mass of one object, you double the gravitational force. If you double both masses, you quadruple the force. But, and this is crucial, if you double the distance between them, the force becomes 4 times weaker. Triple the distance, and the force becomes 9 times weaker. This is called the inverse square law. Let me give you a concrete example. You weigh whatever you weigh because you're about 4,000 miles from Earth's center. If you could somehow stand 8,000 miles from Earth's center, twice as far, you'd weigh 1/4 as much. At 12,000 miles out, you'd weigh 1/9 as much. The force drops off fast. This explains why astronauts float in space stations. They're not beyond gravity. They're only about 250 miles up, and Earth's gravity at that height is still about 90% as strong as it is down here. They float because they're in continuous free fall, along with their spacecraft, falling around the Earth in a circle. It's like being in an elevator that's plummeting toward the ground, except the ground keeps curving away beneath them. Newton's law also explains why the moon orbits Earth instead of flying off into space. The moon is moving sideways at about 2,300 miles per hour relative to Earth. Without gravity, it would shoot off in a straight line, but Earth's gravity constantly pulls the moon toward Earth's center. The result? The moon falls toward Earth, but Earth's surface curves away at exactly the right rate to keep the moon falling in a circle. It's been falling toward Earth for 4.5 billion years and will keep falling for billions more. Same thing happens with Earth around the Sun, except Earth is moving at 67,000 miles per hour, and the Sun's gravity is doing the pulling. We're all hurtling through space in a controlled fall. But here's where Newton's beautiful, simple law starts to crack. In 1915, Albert Einstein discovered that Newton was wrong about what gravity actually is. Newton thought gravity was a force, like magnetism or the push of your hand. Objects with mass somehow reach across empty space and pull on other objects. But Einstein realized this creates a weird problem. How does the Sun know where Earth is right now? Light takes 8 minutes to travel from the Sun to Earth. If the sun suddenly vanished, we wouldn't see it disappear for 8 minutes. But according to Newton, we'd feel the gravitational effect instantly. Information would travel faster than light, which Einstein had proven was impossible. Einstein's solution was radical. Gravity isn't a force at all, it's geometry. Imagine space as a stretched rubber sheet. Now place a bowling ball in the middle. That's the sun. The heavy ball creates a dip in the sheet. If you roll a marble nearby, that's Earth. It doesn't travel in a straight line anymore. It curves around the dip. The marble isn't being pulled by the bowling ball. The curved shape of the sheet itself guides the marble's path. Einstein said massive objects like the sun curve the fabric of space and time itself. What we call gravity is just matter following the straightest possible path through curved spacetime. When you drop your phone, it's not being pulled downward. It's following a straight line through space that happens to be curved by Earth's mass. This sounds like science fiction, but we can measure it. GPS satellites have to account for Einstein's curved spacetime, or they'd be off by miles. Light from distant stars bends around the sun during solar eclipses, exactly as Einstein predicted. We've detected gravitational waves, ripples in spacetime itself, when black holes collide billions of light-years away. But Einstein's theory creates new mysteries. It predicts that 95% of the universe is made of dark matter and dark energy that we can't see or detect directly. We only know they exist because of their gravitational effects. Dark matter holds galaxies together. Dark energy is accelerating the expansion of the universe. We have no idea what either one actually is. And Einstein's gravity breaks down at the quantum level. Inside atoms, gravity is so weak compared to other forces that it's essentially irrelevant. But physicists are desperate to find a theory of quantum gravity that explains how gravity works at the smallest scales. Some think space itself might be made of tiny, vibrating loops of energy called strings. Others think gravity might leak into hidden extra dimensions. Nobody knows. So why should you care about humanity's 400-year struggle to understand gravity? Because gravity shapes your life in ways you probably never think about. Your height depends on gravity. You're about half an inch taller when you wake up than when you go to bed, because gravity compresses your spine during the day. Astronauts grow up to 2 inches taller in space, then shrink back down when they return. Your blood pressure depends on gravity. Your heart evolved to pump blood upward against Earth's pull. That's why you get dizzy when you stand up too fast. Your cardiovascular system needs a moment to adjust. In space, astronauts' hearts actually shrink because they don't need to work as hard. The food you eat exists because of gravity. Stars form when gravity pulls clouds of hydrogen gas together until they're dense and hot enough to fuse into heavier elements. When massive stars explode, gravity helps scatter those elements, carbon, oxygen, iron, across space. Eventually, gravity pulls that enriched material together to form new stars, planets, and ultimately, life. Even your sense of balance depends on gravity. Inside your inner ear, tiny crystals rest on hair-like sensors. When you tilt your head, gravity shifts these crystals, and your brain interprets the signals to figure out which way is up. This is why spinning makes you dizzy. You're confusing your gravity sensors. The internet depends on gravity too. Those GPS satellites that help you navigate, they experience time slightly differently than you do because they're in a weaker gravitational field. Einstein's relativity predicts that time runs about 38 microseconds per day faster for the satellites. That sounds tiny, but GPS needs nanosecond precision. Without correcting for gravitational time dilation, your GPS would be off by about 6 miles after just 1 day. Climate change is measured using gravity. NASA's GRACE satellites detect tiny changes in Earth's gravitational field to track how ice sheets are melting and groundwater is being depleted. When billions of tons of ice melt in Greenland, it actually changes Earth's gravitational field in a measurable way. So what is gravity? After 400 years of investigation, the honest answer is we're still figuring it out. Newton showed us it's a universal force that follows precise mathematical rules. Einstein revealed it's the curvature of spacetime itself. Modern physicists suspect it might be something even stranger, perhaps connected to the quantum nature of reality in ways we can't yet imagine. But here's what we do know. Gravity is the reason you exist. It built the stars that forged the atoms in your body. It holds the planet together beneath your feet. It keeps the atmosphere from floating away into space. Right now, as you sit there, 6 trillion kilograms of Earth are pulling on every atom in your body with a force perfectly calibrated to keep you comfortable, safe, and alive. The next time you drop something and watch it fall, remember, you're witnessing one of the universe's deepest mysteries in action. We can predict exactly how that object will fall, we can use that knowledge to navigate spacecraft across the solar system, but we still don't fully understand why it falls at all. And maybe that's the most beautiful thing about gravity. It's simultaneously the most familiar and most mysterious force in your daily life.